Was this question in your textbook?
Yeah, on the textbook.
Okay, I can look at it after.
Yeah, that's okay. Thank you so much.
All right, shall we begin? Okay, it's not many people today. Must be some events or something happening. Was it like that last week as well? Okay. So, welcome back, and I'll be here for next 3 weeks. So, week 6, 7, and 8, before David takes back for the power amplifiers. So, this is a relatively easier section of the unit: nonlinearity, mixes, and then power amplifiers. So some of you find that 376 is much harder than 275. It's not much harder. It is built on top of 275. So once you have the fundamentals strong, correctly understood, then the 376 material becomes easier. So I want to make an announcement which might make many of you happy. Is that in the final exam, so David and I, we have decided 80% of the questions will come from either assignments or practice questions uploaded, or pre-lab questions, or examples given in the class. Okay, so 80%. So the remaining 20 may be slightly different. And we have talked about N-type MOSFETs, N-type or NP and BJTs. So in the exam also we won't ask PNP and P-type MOSFETs because it seemed to confuse many people seeing it, even though it should be very similar. So hopefully you are happy with that. So now you can earn 80% marks with no problem. Okay. So online quiz, this time it was quite easy. Many people scored 100. A few people scored 50. That means they're not even looking at the answers, just ticking, and by chance, it's just chance that you get 50. One of the most frequently frequent made mistake is this last question: a BJT amplifier can be treated as a linear system if what is the answer? Yeah, the input amplitude must be much less than the thermal voltage, right? It's the 25 millivolt.
Less than the terminal voltage is really smaller than the VDE on, so the BJT will not work.
Yeah, exactly. You're right. That is why we have the DC bias. So keep it on, and on top of that, we apply this voltage, right? So if there was no DC bias, then it is not enough to turn the BJT on. So I hope you all gone through the videos and learned about harmonics and what happens. Just to recap what happens. So if you have a frequency of 2 kilohertz, that frequency is called a fundamental frequency, and or the first harmonics. So you can have multiple higher harmonics of if you multiply with 4 kilohertz will be the second harmonic, multiply with 6 kilohertz will be the third harmonic, and 8 kilohertz will be fourth harmonic, and so on. So you can have infinite number of harmonics, depends on what kind of system you have. Okay, all frequencies above the fundamental frequency, they are collectively called higher harmonics. So you tell me, are harmonics good or bad? Who says it's good? Nobody. So there is a saying in engineering, or mostly in communications engineering, one person's signal is another person's noise. So when you design a communication system, you get static. Have you heard this white noise, static white noise? So if you talk to a radio astronomer, that is his or her signal. So they are researching about the Big Bang and the distant galaxies using that signal. But for a communication engineer, that is a noise. And if you talk to that person, your communication, your signal is actually a noise for that person when in this big telescope. So harmonics are good and bad, so depending on your application. So if you have a 2 kilohertz and if you want to generate a 4 kilohertz, what would you do? You need to rely on harmonics to generate that. Okay, so there are applications. So we will look at mixers as one of the application for using that higher harmonics or a modulation or intermodulation. So we'll learn about the basics this week, and we will go into mixers in the next 2 weeks. So I just made a small experiment enhancing the harmonics of the recording of my voice. I don't know if it will play here. Let me check. No. This is my voice. This is my voice. So the first snippet of voice was my recorded sound, and I enhanced the harmonic contents in that signal, and produced the second part. So you can see the second part is highly distorted. So if someone who knows me hear that sound, wouldn't believe it is me, could be anybody. So all the pitch, tone, and amplitude, everything has changed because of these high harmonics. So it is not a origin or a truthful reproduction of my voice. Okay, it's quite distorted. So that's the reason why we don't want harmonics in a amplifier. Okay, you see how it affects. We'll play because
This is my voice. This is my voice.
Yeah. So if you have a amplifier with a very low quality of design, so your voice reproduction won't be that good. But this amplifier in this room is quite good because I can feel that you are hearing my voice. Even if I speak without these amplifiers, it'll be same quality. Okay. And that quality is a design parameter. So human voice is between 20 hertz and a male voice is somewhere around 2500 kilohertz. And so this amplifier is designed for a human voice. So if you make a really high frequency, if I play a violin here, which contains a lot of frequencies beyond a human speech, maybe this amplifier system is not designed for that. And that will create, you have seen in the lab, it has a frequency cutoff on either side. So it'll go to a much higher frequency. Your sound quality or the music quality will be low. So that's why there is a special branch of engineering called acoustic engineering, where you design the architecture and also audio systems all catered for that particular application, right? Okay, so another example to show you what different sine frequencies can do. So here, this is a video recording from YouTube, a synth school. It shows different frequencies, different sine waves, and
you can see 2, we're not mixing inside, we're skipping it, straight to 3. And voila, it starts to look like a square. We skip the 4th harmonic, 5th we add in, we skip the 6th, we add the 7th, and so on. Let's look at the same thing on the frequency analyzer. Here is a saw wave. This is our fundamental frequency, and now we're going to add the overtones.
Except for the last part. So it shows you when you have a square wave, it's a combination of so many sine waves inside. And they're all odd components of sine waves, the odd frequencies. So if you have a 2 kilohertz square wave, that means that square wave has a 2 kilohertz and the odd multiples of 2. That means 2, and then next one would be 6. Yeah, and the third one will be 5 times, 10 kilohertz, and so on. So, and a triangular wave will have all the frequencies, like 1, 2, 3, 4, 5, everything. Okay, so it's quite different. So so we are basically looking for a system's response with a single sine wave input. And sine wave is, we choose sine wave because that's the simplest waveform. It has only a single frequency. That's the purest wave that we can have. So if you take a square wave and put it as an input to the system, what will happen is, because now you're seeing the square wave has multiple frequencies starting from fundamental to quite high frequency, the system responds to different frequencies different way. So the fundamental frequency will have one gain, the higher harmonics will have different gains, right? So the output will be completely distorted. So it wouldn't look like a square wave, it would look like a really different shape compared to a square wave. So we use sine wave as an input for many systems because that's the simplest to analyze. Okay, here just that concept, a sine wave is a pure frequency, a single in the frequency domain, a single peak. You have seen this in the lab when we were playing with the high frequency response of MOSFETs and BJTs. And when you have multiple frequencies, so here you have three components, n equal to 1, 2, and 3. If you look in the time domain, it may look like a sine wave. It's really hard to distinguish. But if you in the frequency domain, you can see the really clear three peaks or three frequencies there. So that's one reason we commonly use FFT to find out what are the frequency components in the final wave. So what's wrong with harmonics? It causes signal distortion. If you're going for a true amplification of a signal, it is not good. So it causes interference. So if you have a system working at 10 kilohertz and somebody else have a system working at 30, 40 kilohertz, you shouldn't be talking to each other. There should be no interference. But because you are generating not just 10 kilohertz, but also if your system is nonlinear, you will be creating multiple frequencies of 10 kilohertz, and you will be creating 40, 50, 60, 100 kilohertz without intentionally. Not intentionally, but without your knowledge, you might be creating all these frequencies, and it will get affected. The other equipments will get affected by your radiation of these frequencies. So that is called electromagnetic interference, and it is quite bad when you have sensitive applications like medical applications, defense, and quite sensitive equipments like space electronics. So all these interference are quite bad. So the harmonics can cause these interference. So another issue is heating, but only in high power systems, like when you have a mobile tower generating these signals so that you get signal in your mobile. So in those applications, you are creating like hundreds of kilowatts in this antenna, and every unwanted harmonics that generate will be dissipated as heat, and this is quite a large amount of heat. So that's really bad. So emission is the same as the interference. So if through emission you lose a lot of signal power. And sometimes this causes instability. So if you have a circuit designed for a particular frequency range and you have generated some harmonics that have a loop back, and that can create the oscillations and ringing in this. So you have seen ringing in, so this is a different context. You have seen ringing is if you put a microphone in front of a speaker, you get a howling sound, right? So you just get a one single frequency very high, which some of you must have seen in 275 plus early beginning of the year. The whole room you start to ring because my voice from the loudspeaker is picked up by the microphone and keep amplifying that. But that has nothing to do with harmonics, but that just show you what kind of oscillations can happen. So also, the power lines. So in Australia, we use 50 hertz, 230 volt AC power supply. So it is 50 hertz, but the power lines and all can radiate multiples of 50. So sometimes you have an electronics, sensitive electronics device here. It can pick up 100 and 150 kilohertz from the power lines because those are the second, third, and higher harmonics. So you need to have proper design consideration to avoid all that frequencies. You must have seen this ferrite beads in your laptop chargers and maybe telephone chargers and several electronics. So in this context, you can say, yes, they are there to prevent those harmonics from coming in and also prevent harmonics generated by your equipment from reaching outside or going into the power lines. So those are some coils, some low inductance values that will convert, or that will pick up the, or that will convert the high frequency noises into heat. So it'll absorb the high frequency. Okay. Any questions so far? It's the easy bit. Okay. Now we talked about harmonics. We talked about my voice get distorted, but that's not the way engineers talk. We need to talk in numbers, right? So you can't say, oh, that signal is more distorted than the other, but what does that mean? So how do you say that the signal is this much distorted? So we have a few new terms. So the new terms, one is a fractional harmonic distortion, and the other one is total harmonic distortion. So if you get a signal, you need to be able to see, or you need to be able to find what is the fractional harmonic distortion and what is the total harmonic distortion in that signal. Can anyone guess, even before going into the definition, what is the fractional harmonic distortion and total harmonic distortion of a sine wave? If the input is the sine wave and the output is the same sine wave, what is the fractional distortion? I know that you don't know this definition at all, but if you have a pure sine wave input and the same pure sine wave is going as the output, what is your total harmonic distortion? 0. Your fractional harmonic distortion? 0. It's all 0. It's no distortion, right? So, it has something to do with the higher harmonics, higher frequencies. So let's look at it one by one. By definition, the fractional harmonic distortion is the ratio of the amplitude of the harmonic to the amplitude of the fundamental. Okay? So we define, we write it as HD, harmonic distortion. HD2 is the fractional harmonic distortion of the second order, or the fractional second harmonic distortion. And HD3, which is the amplitude of the third harmonic divided by the amplitude of the fundamental, is the third harmonic distortion. Okay? And so on. So if nth fractional harmonic distortion would be the amplitude of nth harmonic divided by the amplitude of the fundamental. Right? Any questions on the yeah?
These harmonics, as we are calculating, these are in time domain, right? We are harmonic distortion.
These are in time domain, but we can't really. So if you have a time domain signal, you can't really see that distortion. So usually you go to the FFT or the Fourier transform, and then find out what is the amplitude for each component, each sine component, right? So you saw here we have 3 components. So if you just had the time domain signal, you could do nothing with that, okay? But when you look at the frequency domain, you know that you have 3 components, 3 frequency components, and if you want to find the fractional distortion of the third order, or HD3, you would look at what is the amplitude of the 3 omega and divide it by the amplitude of omega, which would be around 5.5 or no, what is it? 6 divided by 10. Okay? So that'll be HT3, and HT2 will be what, 8 divided by 10 from that. Yeah. But if you just look at the time domain, what can you do? Nothing, right? Okay, so let's say we have a system with the output like that. Output is A0 plus A1 V input plus A2 V input square, and so on to higher orders. And if it's not U, it's a V, VI is a pure tone, which is a single sine wave, V cos omega t. So we use sine and cos as interchangeably because they are essentially the same. Sine theta is cos 90 minus theta. So it's not just a phase shift. Both are the same. So if you have a pure tone V cos omega t, how do you find? So how do you find the output? So what you do is you just, not there, put this equation for VI into the equation for the output, and you get a big equation like that. So here you will see that you have higher orders of VI. So A naught is there. Now you have A1 VI. Let's do something. Let's derive that. Okay. Okay, so the output was A0 plus A1 VI plus A2 VI square plus A3 VI cube plus and so on. Okay, and VI is equal to V cos omega t. Right? So how do you write V naught? V naught is equal to A naught plus A1 V cos omega t plus A2 V square cos square omega t plus A3 V cube cos cube omega t plus so on. Okay, now these are okay, but here you have a square omega t term. So you know that cos square theta is 1 plus cos 2 theta divided by 2. So that would be A square V square times 1 plus cos 2 omega t divided by 2. So that is this term. Now how about this term? Cos cube theta. That is 3 cos theta plus cos 3 theta divided by 4. That is cos cube theta. Okay? And we have A3 V cube. So that is omega t. That is 3 omega t. So if you bring all the omegas together, you will have A naught, that is the DC part of the output, and now you have A1V, and then you have plus A3 V cube divided by 4 times 3 cos omega t. You see where it comes from? It comes from this omega t term here and the omega t term here. So those are the coefficient or the amplitudes for cos omega t. And you go again to look for cos 2 omega t, which is a2 v square divided by 2 cos 2 omega t. Where do you go? Oh. It's all gone, sorry. All right, let's start again. Hope it's not too boring. So we have V naught is equal to A naught plus A1 VI plus A2 VI square plus A3 VI cube plus so on. Because we do it because once it is important to do all the questions in this topic. Okay, and you may be able to get 1 or 2 questions like that in the exam or assignments coming, right? So it's quite simple. It's just you have a mathematical formula for cos cube theta and cos 2 theta. So just putting them in this one, just testing your focus of whether you can write an equation without making a mistake down the line when you work on it for 5 minutes. Okay, but it's relatively quite simple. And your VI is equal to V cos omega t. So V naught is equal to A naught plus A1 V cos omega t plus A2 V square cos square omega t plus A3 V cube cos cube omega t and so on. So these two terms, same, we want to, the cos square, we want to change it to a single order. So now it is a square term. We want to have it all in the order of 1. So we'll write it A2 V square 1 plus cos 2 omega t divided by 2. And this term, we will change it to the first order 2. As cos cube omega t can be written as 1 by 4 3 cos omega t plus cos 3 omega t. So finally V naught is equal to, let's take the 0th order of omega, which is the DC part. DC part will be A0 plus, is there another DC part somewhere? Yeah, there are other DC parts. You see here, 1. So there is no omega there. That means it is not frequency dependent. So that's a DC. A2 V square divided by 2. So that's the DC part. This is the DC part because we stopped at V3. So if we had a higher powers there, the DC will have more terms here, right? So we stopped at the third order. So it'll have a higher, more terms in the DC part, but it'll have a lower amplitude because it'll go from V square to V cube, V power 4, V power 5. And if V is less than 1, slightly less than 1, that means all the higher powers will go down really quickly. Okay? And now the term for omega t. So we have one here and we have one here, right? So that is A1V plus A3V cube times 3 divided by 4 cos omega t plus, and now cos 2 omega t is here, A2V square divided by 2 cos 2 omega t plus A3V cube divided by 4 cos 3 omega t plus so on. So the terms ended here. So here also you will have multiple terms added to that. But they ended because we only consider up to the third order. Okay? So now coming back. So I told you that the harmonic distortion HD2, HD3 are the amplitude of, so HD2 is the amplitude of the second harmonic divided by the amplitude of the fundamental, right? So when you have an equation like that, V0 is equal to the DC part plus the cos omega t, which is the fundamental, the second harmonic, the third harmonic. So if you want to find HD3, the amplitude of the third harmonic is this one, and the amplitude of the fundamental is this one. So find the ratio of that. So here, just for simplicity, we have not considered the V square term. So we just chose the first term, A1, and here is A3V divided by 4. So one thing to note here is HD2. Can you see how you can find HD2 from this big equation there? So HD2 is the amplitude of the cos 2 omega t term divided by the amplitude of the cos omega t term. And the amplitude of cos 2 omega t term is this one, A2 divided by 2 V square. And the amplitude of the cos omega t term is just A1 if you ignore the V square term. So when you find the ratio, you will find half of A2 divided by A1 times V. Okay? If you do the same thing for the HD3, which is the third harmonic fractional distortion, you get this, but it is dependent on V square. Okay? So that is important for us. So what it says is when voltage is quite small, HD2 has a much higher impact than HD3, right? Because HD3 has V square, and when the voltage is small, when you square a small voltage, it becomes even smaller. Like if you have 0.1 and you square it, you get 0.01, which is much smaller than 0.1. So HD3 is much smaller when V is quite small. But as V start to increase, or the input amplitude start to increase, HD3 grows faster than HD2. Because SD2 grows linearly, because it is that the term is voltage, it's a single order, but SD3 grows in a square law fashion. So if voltage doubles, SD3 becomes 4 times because that's the v square term. So HD3 increases more rapidly than HD2, and it becomes a problem. So HD3 is an important fractional distortion quantity that people.
Isn't they're taking the amplitude A304 VQ divided by A1?
So A3 HD3, yeah, A3 V cube divided by, yeah, A1V, yeah. So we ignore that part. So when you have like A plus B and B is very small, so you just ignore this. Only when it is a plus sign, a sum. But when you have a multiplication or a division, that small part becomes really important. So that's why you may wonder why sometimes we ignore v square and sometimes we take v square. Okay? So that's the answer. So if you have a sum, a plus b, or sum with v plus v square, and v is less than 1, you can ignore this. But when you have a ratio of v square, you cannot ignore that. Okay? Because division by a small number creates a large number, and multiplication by a small number creates a small number. But sum with a small number doesn't affect much. And subtraction as well doesn't affect much. So that's why we ignore this part. So it's A1V, and that's why we have V squared term. Now you can imagine when you have SD4, it will have a V cube term in that. Okay? So that's what's shown here. So this is the input voltage V, and this is how much the harmonic, what is the percentage of harmonic distortion. You see at the lower voltages, SD2 is more. And as the voltage increases, the SD2 increases linearly, but SD3 increases in a square law fashion. So it's increased as square. So the slope is much higher than SD3. And if it goes like that, it will overtake SD2 at some point. But after the voltage is more than 1, it's more complex than that. So it both kind of saturates. Yeah. Any questions on that? Okay, let's do a small problem. So we have a output equation, V naught is equal to Vi plus 2Vi square, and your Vi is 2 sine 50t, which is a sine wave with a frequency of 50 divided by 2 pi hertz. So you need to find the second order and third order distortion, SD2 and SD3. Try to do it, and if you had to make mistake, this would be the right place to make mistakes, not in the exam hall, not in the assignment. Okay, we got only four people got the answer. This should be, you should be able to find it in this time. Okay, I give you 30 more seconds and we'll move on. Let me know if you find it difficult or you're stuck somewhere. So in the exam you will be given the formula for cos square and cos cube if you need to find it. All right. Okay, I'm going to lock it. So if you couldn't find it now, try to find it at home. If you find it difficult, ask me how to find it. But it's quite simple. Replace that with VI. Maybe we'll do it here. So, now what happened? So V naught is Vi, which is 2 sine 50t plus 2 Vi square, which is this square, which is 4 times sine square 50t. Okay, that's the first step. So just leave that alone because that's in the omega t term. If you expand this one, you get, this is 8 sine square 50t, 1 plus cos square, no, cos 250t or cos 100t. The bracket is there. So when you write V naught, let's write the DC term first. 8 divided by 2. 1 minus. All right. Okay, you got that one's right. Yeah, so if you write V naught, what do you find? Let's write DC first. Is 8 divided by 2 is 4. And now the first the fundamental or the first harmonic is 2 sine 50t, and the second harmonic is minus 4 cos 100t. So if you want to find HD2, is this divided by this, right? That is minus 4 divided by 2. But the harmonic distortion is, we usually say without the sign, we just take the amplitude because sign doesn't matter. You're not talking about the signal output, it's just a distortion, percentage distortion. So it is equal to 2 or 200%. Okay, in percentage it will be 200%, or ST2 will be 2. If you ask to represent it in percentage, you multiply with 100, and that is the percentage. And how about ST3? It is 0. It's easy because there is no cos 3 omega t term, so 0 divided by 2, 0 or 0%. Yes?
What happens with at the end of the initial formula, there will be sine of 100t. If I plus more sine of 100t, what is the HD at this time?
Plus a sine of 100t.
Yeah. So I will have cosine of 100t plus sine of 100t. So what is the HD at this time?
Sorry, I didn't understand the question. Sorry.
Yeah, the formula of V0 I plus more sine of 100t
Yeah.
I will have sine 100t and cosine 100t. So which I will should I take for this one to find out the second.
Oh, so you take both. You take the sum of the both, because both are actually same. So sine and cosine, they are actually the same. So you take both of them.
Some of the amplitude.
Yeah.
So if we find
4 plus 1 like in this one like 4 plus 1.
Yeah. If you have 4 sine omega t, so you'll have 4 plus 4.
Because sine and cos is different in phase, do we take it like 4 minus 4 or 4 plus 4?
No, its phase is not 180-degree phase difference. It's a 90 phase difference, and you won't see sine and cos in the same this one. Yeah. So it will be either cos or it'll be the sine. Right. Yeah. There was another hand. Oh, okay. So another term is total harmonic distortion. Okay. So total harmonic distortion is defined, or total harmonic distortion by root mean square, which is shown it here as R, is the ratio of the sum of all harmonic components to the total signal strength. Okay, so if you have that V naught like that, so total harmonic distortion is the sum of the amplitude of all harmonic part, or the higher harmonic part, which is 2 omega t, 3 omega t, and so on, divided by the total signal strength, except for the DC part. Okay, so in signal, when we talk about signal, we just don't consider the DC. Just think of it going through this coupling capacitor, which just filters out all DC and just the signal. So in this case, when you have A naught and V cos omega t and V2 omega cos 2 omega t, V3 omega cos 3 omega t, you will see that the total harmonic distortion is the root mean square of all this part divided by the total signal. And when you say the total signal, that includes the harmonics. Okay? Yes? You have any question? Okay, so what could be the highest value of total harmonic distortion in percentage? Yeah, in 1 or 100%, right? It cannot be more than 100% because the denominator is always higher than the numerator. Okay, the worst case is you don't have the fundamental frequency part, so the numerator and denominator becomes equal, so that becomes 100% distortion, total distortion. Okay, so these are two main terms that we that we use when we talk about nonlinearity and mixers and so on. Okay. So in the same problem that we have done before, can you find the total harmonic distortion of the signal in the previous problem that you did? So what is it? Does anybody have any answer? 69? Any other answer? 81? So how did you find it? So this is omega t term, right? And this is 2 omega t term. So total harmonic distortion is the strength of, or the root mean square of all the amplitudes in the harmonics, which is here in this case is just 2 omega t, 4 square, right, divided by square root of the total signal except the DC part, 4 plus, or 2 square plus 4 square. That is 4 divided by root of 20 times 100 in percentage. How much is it? 89.4%. Okay, so the problem may look simple, but there are a lot of chances to make mistakes. Okay, if you just look at it, okay, yes, I can do that, but when you do it, you might make mistakes. So just make sure that you do some practice problems yourself. Okay, where did you make mistake when you said 69 and 81? Oh, you didn't do the square. Yeah, okay. And how about you? You said 69. No, you didn't. Who said? You said 69. Okay. So yeah, it all will cost you mark, not here, but in the exam hall. Okay, make sure you do it yourself. So another term which is very close to what we're going to learn in mixers is intermodular distortion. So everything we talked about till now here is there is a nonlinear system. We are giving an input and we are checking the output. So like a diode, here is a diode and it is DC biased, and we are looking at the output. So we are giving an input here, Vi, and it is passing through this nonlinear system and coming out as output. And because of this nonlinearity in the diode, we find extra components in the output. That's what we looked at. So intermodulation is something different. In this one, we are going to apply two frequencies, F1 and F2, or omega 1 and omega 2, and see how they mix together due to the nonlinearity of the system. Okay, so this is something we are going to use in mixer. So this is not a single frequency. There are two frequencies. And you said when you have a single frequency omega, you have harmonics 2 omega, 3 omega, 4 omega, and so on. And intermodulation happens when you have two frequencies, omega 1 and omega 2. In the output, so if you give this to a nonlinear system, can you, okay, before going into the details, can you guess what will be the output? Of course, there will be harmonics from each individual signals. So there will be omega 1, there will be 2 omega 1, there will be 3 omega 1. And again, there will be omega 2, 2 omega 2, 3 omega 2 components. And there also will be the sum and difference frequencies. There will be omega 1 plus omega 2. And there will be omega 1 minus omega 2. And there will be 2 omega 1 minus omega 2. And there will be 2 omega 1 plus omega 2. So there will be plenty of frequencies there. So this part, this modulation of the two different frequencies, that is called the intermodulation. Okay, that's similar mechanism as harmonics, but so you can say intermodulation is same as harmonics when omega 1 equal to omega 2, right? So omega 1 plus omega 2 becomes 2 omega, and omega 1 minus omega 2 becomes 0. So, and so on. Okay, so both are the same mechanism, but when the two frequencies are different, you call it intermodulation. And we use it in mixers to generate more frequency components. So if you have 100 megahertz, you have 80 megahertz. You want to generate 20 megahertz. What would you do? You just put them together and you can make 180 and you can make 20. Right? So if you've done the problems for the harmonics, you can do the problems for this one. Just gets a bit more complex because now we have two frequencies to deal with. Okay, so here the input contains two frequencies and two amplitudes. So it's V1 cos omega 1t plus V2 cos omega 2t. So there are two frequencies, omega 1 and omega 2. And let's say we put that through a system with same distortion. So it's not linear, it's DC plus VI square plus VI cube and so on. It's time consuming to write it down one by one, but you can imagine how it would be. So the first term, VI is the same, VI square. So what do? You just put the whole thing square. So that is same a plus b whole square, a square, which is here, b square, and then 2ab. Right? And now you have a square term, which you know how to expand it. 1 minus cos 2 omega t divided by 2. Same thing happens here. So what will happen here? So this is in the same form as cos A, cos B. So that is half cos A plus B by, what is it? Half cos A plus B plus cos A minus B, right? So that's cos A plus B is cos A, cos B minus sin A, sin B. And cos A minus B is cos A, cos B plus sin A, sin B. So what is cos A, cos B? So cos A, cos B is half of cos A plus B plus cos A minus B. Right? So that is where the omega 1 minus omega 2 and omega 1 plus omega 2 comes from, because of this term. See, in the time domain, this is the product of two signals, the cos omega 1t multiplied with cos omega 2t. But if you look in the frequency, what happens is this is omega 1 plus omega 2, and that is omega 1 minus omega 2. Okay, now you see where the difference and some frequencies are coming. And those are not harmonic, so you cannot get omega 1 minus omega 2 by multiplying either omega 1 or omega 2 with an integer. You may be in some special cases, but not always. It doesn't have to be a multiple of either of the frequencies. So you generate a completely new frequency through intermodulation, right? And same thing happens in the higher terms, in the VI cube term. So it's more complex. Now it's A plus B, the whole cube. So that is, does anybody know what is the expression for A plus B, the whole cube? A cube plus 3A square B plus 3AB square plus B cube. Now we have square term and multiply with this one. Yes?
For the exam, do we have to have this now?
No, if no, there will be a formula sheet if you need to do any question with the cube or any. So exam, we do we solve the questions first, and whatever formulas are needed will go into the formula sheet. So you don't have to remember all this. Right. But it's not the worst thing to remember. A plus B, the whole cube. I don't know. Have you memorized the Schrodinger equation? So here you see you have a square term that you know creates 2 omega frequencies, and then you have a multiplication that you know creates plus or minus. So just by looking at it, you know this will create a 3 omega component. This will create a 3 omega component, and this will create 2 omega 1 plus or minus omega 2 component, and this will create 2 omega 2 plus or minus omega 1 component, right? So those are here, I marked it in a different shades. The pink shade shows the intermodulation, and the gray shade shows, gray also shows intermodulation, but there are unshaded parts which are the harmonics. Okay, so this is the fundamental frequency, this is another fundamental frequency, this is a harmonic, this is another harmonic, and this is intermodulation, 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 intermodulation. So the output contains the fundamental frequency, sorry, the DC part, the fundamental frequency, and harmonics and intermodulation. So it's like a jungle. It's everything in there, all kinds of frequencies. So here in this case we have omega 1 plus omega 2 or omega 1 minus omega 2 as intermodulation in the second order, and third order we have 2 omega 1 plus or minus 2 omega 2 as well as 2 omega 2 plus or minus 2 omega 1 here, right?
Only omega 1 or 2 omega 1 plus or minus 2 omega 2?
Sorry, what was that?
Omega 2 plus or minus 2 omega 1.
2 omega 2 plus or minus omega 1 and 2 omega 1 plus or minus omega 2. So this is IM3. So one method I found to memorize it quickly is just check 2 plus 1, 3. And here 1 plus 1, 2. So IM2 and this is IM3. And I know that IM4 would be either 3 omega 1 plus or minus omega 2 or 2 omega 1 plus or minus 2 omega 2 or omega 1 plus or minus 3 omega 2. Okay? So like that. So I added these two, it's 4 in all these three cases. So the importance, we could have stopped at IM2, but we also need to see IM3 because that's of special interest to us. You see here we have a range of frequencies, the two frequencies F1 and F2 here, and when you pass it through a nonlinear system, you get all these frequencies shown in red and the pink, red and green. They are all frequencies generated as a result of it passing through a nonlinear system. And you see the IM3, both IM3s are very close to the actual frequencies. So it's very difficult to remove IM3 sometimes because their frequency is quite close to the signal frequency that we want. If it was far away in frequency, we could use a low pass or a high pass filter to cut it away. But if it is very close to our frequency that we are interested in, it is quite easy for it to get through this low pass filter that you design, right? So that's quite important. I've given an okay, here is an example of two frequencies, F1 and F2. So F1 is 1 gigahertz and F2 is 1.1 gigahertz. So because of harmonics, you will have 2 gigahertz there because that is the second harmonics of 1 gigahertz. Then you have 2.2 gigahertz, which is the second harmonics of the second frequency. Again, you have ST, which is multiplied with 3 of each of the frequency. Then you can have IM2, which is 2.1 gigahertz by adding the two frequencies, 1 and 1.1. you can have 100 megahertz by subtracting these two. You can have IM3, which is 1.2 and 0.9. You see, this 1.2 is much closer to 1.1 than any of the harmonics. Right? So that shows it's why it is quite important. So IM3 is quite important when we design a amplifier system for a nonlinear circuit. Yes?
So what if this 2,000 milliamp, let's say this relation between, for example, if frequency 1 is 0.5 gigahertz and frequency 2 is 1 gigahertz, if there have what's the relation like this?
Yeah, so you will have 0.5, you will have 1, you will have 1.5, you will have 2, etc. because these are the harmonics for this. And you will have 1, 2, 3, 4, 5 gigahertz. And then you will have 1 minus 0.5, which is 0.5, and then you will have 1 plus 0.5, and then 1.5 from 2 minus 0.5, and then you will have 3.5, so on. So you will have some nodes in the system. Okay, do you know what is nodes? So if you have one frequency multiplied with a multiple of that frequency, which is what we are doing now. So in some cases you have 0 frequency, and some cases you have double the frequency. So that's a nodes. That's a frequency node. So you will generate a node like that if you have some system like this. And it's going to be really difficult to remove some frequencies because some of the intermodulator frequencies are exactly like this one. This is an intermodulated 0.5 gigahertz, which is same as your input, which you're expecting at the output. So whatever you do, you cannot take it away because that's exactly coming in the same frequency. So you just have to live with that.
So
Yeah.
will be with more distortion?
It will cause same amount of distortion, but it will make it very difficult to remove it in the output. So when you have, so in the output frequency domain, if this is your frequency, what you want, and here is a noise frequency or a modulator frequency, you can easily design a low pass filter to remove it. But in this case, your noise is exactly same place, so you can't do much. Yeah. Yeah, you have to live with that. You can't remove it. Just have to accept it. And one way to change that would be don't take 0.5 and 1. Okay, so just take some prime numbers like 5 and 7. Okay, so this is just a recap of what you have done, and this is the last topic of today's lecture. So you have checked the nonlinearity, or basically you are looking at the high frequency response of MOSFETs and BJTs. But what you were also looking at was what are the frequency components extra generated in the FFT. And you saw that MOSFET generated 2 major components and BJTs generated much more frequency components, and one was more messier than the other. You tried to remove them by adding a RC filter, right? So I hope you still remember all that. And this just shows why the diode generates nonlinear components, because we know the diode equation. ID is IS e power Vt divided by Vt. Vd is the total input voltage, which includes the DC and the signal voltage, or Vd is equal to the DC part plus the AC part. And if you expand them, you get this part, which is the DC diode current times the signal part. Now you already know it because it was in the lab that you can expand this using that formula. And so far what we have been doing was, in this expansion of e power x, 1 plus x square by 2 factorial plus x cubed by 3 factorial in infinite terms, we assumed x is much less than 1, and then we ignored all these parts. And we took 1 plus x. So that's what we have done here before. That is the linear approximation. And there are some times when we cannot do the linear approximation, or even if you do the linear approximation, the harmonic components are still there, still present there. Okay, so that's what we are studying here. So in reality, it is actually this one. So we took n equal to 1 for the linear approximation, right? So that if n equal to 1, or 0 to 1, or up to 1, that will be id plus id times vd divided by vt. So this is what our linear approximation looked like. But it is actually not only up to 1. There could be 2, 3, only up to infinity. So there are infinite terms. Each term means there is infinite number of harmonics there. So this is what we used, e power x, the summation of different terms in increasing orders. So that, just want to mention Euler's identity. It's quite a beautiful formula in maths. So e power I pi is equal to -1. So e is a irrational number, never ending, never repeating, keeps on going up to infinity. And pi is another irrational number, does not repeat, does not end, keep going. And when you put e power I pi, you get -1.
How is can prove it? All of them are infinity. Never end.
That's the beauty of it. That's why I really wanted to mention it. So you have a never-ending number, you raise to I power the never-ending number, and you get -1s. Yeah, it is weird, and it is quite beautiful. And the pi comes from circles. It has to do with circles. E comes from a completely different field of compounding, or what do you call, like a growth of bacteria. It's all related to E. And I is a term invented by engineers and mathematicians to show is equal to root of -1. No, you can write e power I theta is equal to cos theta plus I sine theta. No, it's not Fourier. It's different, but yeah. So you just need to know this, or it'll be given in the formula. But I just thought it'll be worth mentioning how good it is. Okay. Similarly, in a BJT, you have the output current, or the collector current, IC, is IS e power VB divided by VT. VB is the sum of the DC plus the signal part. And when you expand it, you can change it to the bias, IC bias, times e power VB divided by VT. Again, expand it this way using e power x expansion. And your output voltage is VCC minus IC RC. And you apply this IC into that. You can find that the output voltage also contains so many higher frequency terms in that. Okay? Any questions in that? Okay, diode MOSFET is slightly different because it's not an infinite number of terms in the output, because the MOSFET's equation is half Kn VGS minus VT the whole square in the saturation mode. And we know that the output is equal to negative ID RD, and ID is this one. And if you put VGS is the AC plus DC plus AC, you can expand this to A square plus 2AB plus B square. So when we learned about MOSFET, what we did was we ignored this part, and then we took this part and took the linear approximation, right? If you remember the MOSFET lecture, parts, we ignored this, but we don't ignore this in this section. We will take it as well. So if you don't ignore it, you get the drain current like that, and then you get this extra term which was not there before. And what would be your output? P naught is equal to minus ID RD. Right? And ID has this part, the linear part and the square part, and then you can find the output voltage as well. So that's what we can do here. The last slide, yes. The MOSFET, GM is given, Kn is given. Sometimes you may not be given the GM or Kn. Maybe you're given the VGS and VT, but you can find, if you know one, you can find the other, right? The drain resistance is given. The input is 0.2 sine 500t. What is HT2 and HT3? How do you find it? So you know V naught is negative IDRD, and you have ID. What is ST2? One clue is this one, you can write as GM. Any answers? Zero 0.05 or 5%? Is that what you got? 5%? Who got 5%? 1, 2. Who got 10%? 1. 25? Only 1? Any other answers? 15? 50? 50%? Okay, just goes to show you how many answers can be there for a simple problem. I got 5%. So there are 3 against 1 each. So I don't know, I just did it just before the class, so maybe you want to double check your calculations. So I just did it in 2 minutes quickly just before the class. So must have, but I think it's right. I think it's 5%. What is SD3? Nobody should have any doubts about that. What is SD3? Is 0 because there are no third harmonics there. So SD2 is 0.05 or 5%. Okay, that ends today's lecture. If you have any questions on the assignments, you can ask me. So, who think assignment was tough? Was it really tough or really easy? The assignment one. Was what? Because yeah, yeah. So that's the one of the problem of a computer marking is just you need to have the right answer within that tolerance. Otherwise, you get no marks for participation. But it is justified because it is an open book and you have so much time to finish it. So you can be careful.
Why do you need to your question with the capacitance? Why do you need us to write the answer on the gate bandwidth front end? Why is that?
Oh, so that's a very common notation used in when you design amplifiers, gain bandwidth product, which is the product of the bandwidth and the gain and the mid-band gain. So that's not just for the assignment. The gain bandwidth product is a commonly used parameter to define an amplifier.
Because usually we used to only have the question for bandwidth or gain. We never have something like
Yeah,
gain bandwidth product.
just a product of the two. Yes.
In the assignment, there was a question where we had to write the answer for RP plus RC. So I was thinking that in the RP plus RC, they are in parallel with DCC. So if in that case, should RP plus RC be like serially added or like parallelly added?
RB was not in parallel with RC because they are on the two different sides of the circuit.
But
Right?
the source, the voltage source was from DCC. RP went to the base and RC was raised.
So it is the one side of RB and RC is connected to the ground, but they are in two different parts of the circuit. So it will never be parallel. It's always be in series.
That's what I went wrong.
Okay. Maybe you think too much. Okay, so I'll be here for the next 20 minutes. You are free to leave. Looks like nobody wants to leave. All right, yes. Yes. Oh, that one. Okay, yeah. You can ask that question too.
For the assignment, so that find the 3 dB frequency, that voltage, and so it was written like find the 3 dB, not minus 3 dB. So what we did is like 1 by, instead of 1 by root 2, we did root 2.
Okay. So if you have so do you agree that the mid-band gain is the maximum gain you can have? So if you have a gain of, if you have an output voltage of say 5 volts in the mid-band, do you think any other frequency you can have more than 5 volt output? You won't. So that's the maximum. That's the top voltage, right? So usually it is minus 3 dB, but it is not. It is usually the referred to as 3 dB frequency because negative is understood because positive makes no sense because the mid-band gain is the maximum gain you can have, and it tapers off on both ends, right? So this is 3 dB and 3 dB. So it was the same question as in the lab, and so if you have done the lab and you found the 3 dB frequency, it's quite easy, you know exactly what 3 dB is. So yes, no. It is called a ferrite bead. It's a iron core with a few coil wound on top. So it works like a RLC circuit, right? So your wire is like a conductor, and this one has this coil and a small resistance to it. So it's like an RL circuit. So RL circuit can be used as a high pass or a low pass filter. So this is a low pass filter, which attenuates all the high frequencies. Okay, yeah, here it is. There is some calculation here. If you can have a look. Okay.
Just okay. I have to calculate the overall range, but I think I want to find a general formula to do it because it's just second level. If they are more, it will. So I change it to an amplifier.
Right.
One and I will choose the output like that.
Right.
And so I find the final formula.
Okay, so this is something we will deal with in the system integration thing.
So you see here, this current path, this is not isolated because now this one also have this one. So it's more complicated. So
So you wouldn't be able to use it like this.
Yeah.
Maybe you get a rough answer,
Yeah.
but not exactly same.
So, the only way is that we have to calculate each state. We have to calculate from here to here.
Yeah.
Yeah, there's no other way.
There are other ways using a matrix method. Yeah,
Yeah.
but that also shows.
Yeah, really.
Yeah, it's a bit long. But you can have a general formula. You can design a general formula for all these kind of problems. But making that formula is quite complicated. You can even have a computer program which give you each stage, then you can give the overall. Yeah. So do you think?
Yeah, no, where
Okay. Do you see where you go wrong?
Several questions. Firstly, what's the reason for this question?
So you saw that e power VBE divided by VT, right? So we expanded it as 1 plus x plus, which is VBE divided by VT plus x square by 2 factorial plus higher terms, right? So we assumed
I realized it.
right, this one because this wood will be smaller.
Yeah. I misrealized the
Ah.
question. I think. Input and to the left.
The last one, the 5%. Yeah, this is how it is sold.
So don't understand why. Negative. Oh,
GM. So that is GM VGS plus half Kn VGS square.
But what is the situation in the diode for this question? What will be answer if this is a diode?
Yeah, diode will be the same. Yeah. Because you see in a diode, ID is equal to I0 e power
Your diode has the equation. I think. That's
VD
it.
divided by VT. So the VD should be much less than VT. Oh, you wrote this here, right?
I wrote it. Yeah. Oh, that's it. Yeah, I just missed all this.
Yeah. So half Kn VGS square. Yeah. So half Kn VGS square is VGS is 0.2. And when you square, it will be 0.04, like extra 0 there, right?
So you ignored the big I, like the DC side was ignored.
Sorry, which?
The DC, the big I thing was ignored.
Yeah.
So you just walk through this.
So you can put the big ID as well, but when you look at the signal, just through the capacitor, which the DC part just.
But in diode, there's already have a BIOS.
In the diode,
They already need a
Yes.
BIOS. So, but in the BJT, they need a BIOS.
you need bias for BJT as well.
Yeah. So once we added with BIOS, that should be much more than VT.
No. So bias is completely different. So you remember when we did the small signal analysis,
Yeah.
we ignored all the DC because DC is only to set the Q point.
Yeah.
So imagine in this circuit, you did not have the bias.
Yeah.
Say VD was 0, you will be operating here. So you will be operating like a rectifier, right?
Yeah. I understand. Since I just misunderstood the question. So usually we are we are analyzing the such small single circuit. We always equal all the DC components. Okay.
Yeah.
Usually we have such a circuit like this to show that the transducer. Yes, but how could we analyze a diode to draw such a circuit like a transducer like this? But I can't draw such a Diode.
Yeah, diode you can, just like you did, so it's like a
So like
RD
this?
and a voltage source with VD. Right.
What you mean? I mean that
So
how?
once you have that DC operating point,
Mhm.
then you can replace the diode
As
with
a
the
resistance?
resistor.
Okay.
Once you have the DC.
Oh, I
box,
get it. Oh, I
right?
get it. Yeah. This is done.
And the voltage across the resistor is VD. Yeah.
The question 10.
Yeah.
So, like, I checked the textbook and to find the common the gain bandwidth
Product.
Yeah, product. Yeah. So it was gain times the highest
The bandwidth.
the bandwidth.
Yeah, gain times the bandwidth. So in this question, the lower bandwidth was given,
Yeah.
10 kilohertz.
Yeah.
Then the other one was in megahertz, right? So even if you did not subtract, it wouldn't have made a big difference.
Yeah. So why did I found the
It's because in that one, maybe the textbook was only talking about this kind of response, where you have a response like this. But in this question, you're talking about a product like this. You know, this is coming from the coupling capacitors. You did the lab, right? So if you don't have coupling capacitors, you will have a response like this. But when you have coupling capacitors, the DC, the lower frequency also get attenuated. So you will have two frequencies, FL and FH, and your bandwidth will be FH minus FL.
Okay, so I had to subtract FH.
FL, so that will give you the bandwidth, and then you have the gain, so you multiply them together. Or you may have to change the gain to dB. So when you have the voltage gain, you'd find 20 log the voltage gain, which will give you the voltage gain in dB, and then you multiply with the bandwidth.
One more question is, in the diode situations, the small singular in here, that is positive proportional. One means that voltage rise, the current will be rise. Yes, but what if some maybe have some common this relation is a negative negative relation, but how to analyze such a situation?
Yeah, so it just says out of phase. So when the voltage increases, the output decreases.
Yeah.
So that is in the BJT. That is because we take it at the collector through the resistor. So it is same thing happening when you increase the voltage. The output current is increasing, and when you decrease the input voltage, the output current is decreasing. But when we take the voltage output,
that's the reverse.
when you increase the current at the output, more voltage is dropped across the resistor, and you're getting only what is remaining.
Oh, yeah.
Right.
That's the reverse situation.
Yeah, like if we have to calculate the input differential signal and particular I is given, how do we do that?
Input differential signal.
In a BJT.
Yeah.
And if I is given like
IE is given, yeah. So differential output.
Input differential signal.
Okay, so you're giving across.
Yeah. Two different
Okay.
sources go together.
So there is one IE this way, and I is the other way. So it's like the opposite.
So how do we calculate the input differential signal? Like I is given.
Yeah.
And we need to calculate the input in this interest mix, suppose inside class one question over there.
Okay, so I think if the BJTs are balanced, then IE should be 0. Right? So because one is going up, the other one is.
That would be BI like input voltage, right?
So you have two BJTs.